Hi, physics class. Today we're going to talk about simple harmonic motion. We talked about pendulums yesterday. We're going to talk about them more today. We're going to do or try a bit of a lab involving pendulums. So I'd like you to get your hands on some string and something you can tie to the end of that string for tomorrow. So please look into that. So today's class is going to be fairly theoretical. There's not going to be a ton of math, but I'll put a little bit of an assignment online so you can get a bit more practice. So let's get into this theoretical stuff. So a pendulum, we know it exhibits periodic motion. It just swings back and forth. It's not going to surprise anyone. The force that causes that motion is a component of gravitational force. So check this out. I've drawn a pendulum. This is when it's just hanging freely. That's its equilibrium position. Now, if we raise this pendulum an angle I've called theta, the force that trying to pull it back to its equilibrium position would be this component, right? It's directed toward the equilibrium position. This you call a restoring force, okay? A restoring force is just a force that's pulling something back to its equilibrium position, okay? But what happens is this thing swings and it accelerates until it reaches equilibrium position, but by that point it has a speed that's going to pull it past the equilibrium position, okay, and it'll experience a restoring force back toward, and this just repeats itself, okay. So this is what causes simple harmonic motion, is a restoring force, okay, that is proportional to displacement. All right, so this is the definition of simple harmonic motion. It's caused by a restoring force. So that's a force pulling something back to its equilibrium position. It has to be proportional to the displacement from equilibrium. We'll get into that on the next page here. Again, this is theoretical. Try to follow along. It might be interesting to you. At the end of the day, though, today's stuff won't necessarily be on a test. You will need to know this, though. What causes simple harmonic motion? The restoring force proportional to displacement. Proportional means if I double the displacement, I double the restoring force. If I multiply displacement by 5, I multiply restoring force by 5. Okay? So I want to actually do a bit of an investigation to see if the restoring force, which is gravitational force times sine, is proportional to the displacement, which is this angle theta. Okay? This might be interesting to you. I doubt you've seen some of the stuff we're about to do. So restoring force is Fg sine. It's actually not quite proportional to displacement. Okay, it would be if it was just Fg times theta, but this sine makes it a bit more difficult. So let's just do, let me use scrap paper here. Let's take Fg is just going to be 1. I'm not going to do anything with Fg other than just multiplying by 1. Let's say theta equals 20 degrees. Okay, that would make the restoring force equal 1 times sine 20. Okay, if I just do 1 times sine 20, let me clear all that, I get 0.34. Now let's double it. Double the displacement. Let's see what happens to our restoring force. If it's proportional, then the restoring force should double. Let's see. If I do sine 40, I get 0.64. These aren't double. In fact, I'll just divide. Do sine 40, divided by sine 20. It's times 1.88. So when the displacement was doubled, the restoring force was not doubled. So a pendulum doesn't exhibit simple harmonic motion for these angles. But now I want to show you something really, really cool. Let's take a smaller angle. Let's say theta equals, say, 1 degree. Then the restoring force is 0.017. Now let's multiply that by 2. I'll do sine of 2 degrees. I get 0.0348. This was actually 0.0174. Check that out. By my eye, that looks like it's doubled. Let's just quickly do sine 2 divided by sine 1. It's not exactly times 2, but that's pretty darn close, wouldn't you say? Okay, so this is times 1.9997. What I'm getting at is, well, what did we change? We just made the angles smaller. When the angles are small, the restoring force is proportional, or super, super close. Okay, so how are we going to say this? Restoring force of a pendulum isn't quite proportional to displacement theta, but for small angles, okay, we can assume, and it's a safe assumption, like the difference between the number 2 and this number is so close that we wouldn't make any difference in our measurements. Our measurement tools would introduce more error than this approximation. So for small angles, we can assume it is, okay? There's no real cutoff. Like if I do, let's just try another angle, 5 degrees and 10 degrees. I'm just going to skip to the good part. If we just do sine 10 divided by sine 5, we'll see how close it is to double. It's still really close to double. Or if we do sine 15 divided by sine 5, this would be triple. See how close it is to the number 3. Pretty darn close, but it is starting to diverge. Like if we do sine 30 divided by sine 10, that's quite a bit off from times 3. Okay, so I'm going to say for small angles, maybe less than 10 degrees. Okay, if the angle's greater than 10 degrees, all that means is that the period of a pendulum doesn't quite follow our formula. So this formula really is only valid for small angles. For larger angles, the period actually will be larger than this. And you can search online and see it's some interesting math, but way beyond our abilities to calculate. But adding a larger displacement does make a pendulum, take a longer time to oscillate. It increases the period. Okay, so all I'm going to ask you today is use this formula again and know what simple harmonic motion is. Okay, restoring force is a force that returns something to an equilibrium position. If that restoring force is proportional to displacement, you get simple harmonic motion. The other application we're going to get of simple harmonic motion will be of springs. Okay, so if you have a spring, we'll get into this next week. If you stretch it, well, by Hooke's law, right? Actually, I should just write that. F equals kx. X is the displacement. If you double x, you double f. So springs oscillate with simple harmonic motion, and we'll talk about that next week. I think that's it. Remember, this formula only works for small angles. All right, get yourself some materials to be able to build a pendulum. At the very least, you'll just need string, a piece of tape, and something to tie the string to. Maybe like a metal washer. Okay. Instructions to follow.